Hey guys, welcome back to NCERT class. Here I'm going to consider chapter 12.2.2 and I'm going to give you an example with unbounded region. So remember before we actually covered those first three steps and we didn't touch the step 4 because in our case in the previous video dedicated to bounded region, we actually end up with maximum and minimum value for z that actually becomes the maximum and minimum values. So there wasn't any problem with their objective function z because the largest value for z becomes actually the maximum value and the minimum value stays for the lowest value for z. The polygon was convex. In this case, I'm going to show you what if the region is unbounded. So it might be unbounded from one side, from one half. So let's have a look. So here we need to minimize the following objective function z, which is equal to y minus x, which is subject to the constraints. So in here we have 1, 2, 3, so 5 inequalities that set up the region. Okay, so as in the previous case, we need to start first to find the feasible region of linear programming problem and determine vertices. So that's necessary, and we used to do all our knowledge about how we first construct the boundaries, basically straight lines. Instead of inequalities, we're going to use equations, and that's how we can set up the boundaries. And after that, just looking at the inequality sign, we just have an understanding where is our region. And hence, by combining all those regions that are wanted for us, we actually come to the region that is called feasible, as you remember. So in the programming problem in applied math, this region is called not just wanted, but feasible region, because here actually in real life problems, that's the region. Every single point from that region is a feasible solution. So, and from there, they're actually entrepreneur on a manufacturing, let's say, plant or some, and applied to anything else. So we actually discuss that might be diet problems, there might be sort of logistics problems about transportation, about scheduling. So the owner of the business can figure out which value he wants to get, the minimum or the maximum value. So if he maximizes the profit, obviously he wants to keep the maximum value for his profits, or for the profit of his company. About manufacturing might be the lowest costs. Okay, you understand what I mean. So here we are going to construct 4 lines. So the first line 1, and here we set up 2x minus y equals to negative 6. So we first want to construct that. So I clearly see that 6 is going to be their y-intercept from there. So we've got 1 point, or just simply you can create the list of tables. So take any x value and plug into equations and determine y. So it doesn't matter which way you go. So 1, 2, 3, 4, 5, 6. So we've got 6 and we've got the first point for that line. So another point, it seems to me, if I say, okay, y equals 0, so I got x negative 3. So it's here. That's another point. And here I'm going to connect with the line or with the segment. So which color to use? I'm going to use that one. So that's how my segment line L1 goes. Okay, so what about the region? So y is going to be less. I simply transfer negative y to the right hand side of an inequality to understand y is going to be less or greater. So if I transfer, I'll get y actually less or equal negative 6 transfer there, so 2x plus 6, and I understand that y is going to be lower, so region is below that line, okay? This is L1. Okay, so we're going to go next. This is line 2, 3x plus y, so, oops. So for line 2, for L2, I'm going to use the following equations: 3x plus y equals to 4, from where I can say, so if x is 0, 4 is going to be y-intercept, so that's 4. And what about, so I'm not going to take x, so y equals 0, because in this case I'll get 4 over 3, so not so cool value. So what I'm going to do, maybe, anyway, okay, so 4 over 3 is going to be the case. So, okay, so 4 over 3, it's somewhere around, let me see, so here's 2, so 4 over 3 is going to be somewhere here, okay, so somewhere here, that's 4 over 3, basically it's x-intercept. In here I'm going to connect those 2 points, so from there, yeah, perfect. Okay, so that is going to be line 2, so this is line 2. Okay, so we're moving next, and next one is line 3, which is here. So I'm going to do the same. L3. Oh, by the way, so what about the region for that? So y is more than equal to 4 minus 3x. So more equal, it's basically the top part. So it's here, okay? So that's the region. Okay, anyway, we finalized with the complete region in the end. So what about line 3? 2x minus 3y equals to 12. That's line 3. And from where we can say that if we say y equals 0, we got x-intercept, which is 6 from there. So 3, and again 3, it's going to be 6 here. Okay, so that's going to be 1 point for L3, and we can say that, let's take maybe, so what about 4, 24 over 2 is 12. Yeah, we can set up the list of values for x and y. So it would take 0, we get 6. And what about, it would say x equals to, let's say 12. I'm not going to use just negative values. That's the reason. Okay, so 12 for x. We've got 24 minus 12. 12 over 3 is 4, okay? So when x is 12, we've got 4. Okay, so 3 here, and again 3 here, so that's going to be 12. And y equals 4 is going to be that point. So that's for the line 3, okay? Actually it goes down by taking into account that cases, so that we limit it in the first quadrant, so it means we are here. We're not going to use values below x, so actually I can start from somewhere here. Okay, yeah, perfect. Okay, and this is the line 3. So what about other inequalities? That's okay, that's okay. So the region actually is here. So I'm now going to use, let's take red one. Let's take yellow. It's good. Yeah, I think it's good. So what about our region? So for line, what's about line 3? So y is going to be more equal if you transfer negative 3y to that side. So the region is simply above line 3. So that's why I can, oh, sorry, this marker, I don't like markers here at all because It actually works really, really bad. Okay, so I'm gonna use that one. So probably, let me highlight with this. Let's take that color. Yeah, that's okay. So here is our region. It's here. So as you can see, it's lower than line 1. It's above line 2. So line 2 is here. It's actually above the line 3. But as you can see, it's not opened, right? So as you can see here, it's no, oh yeah, it's much better. Okay, so it's not bounded. It's not bounded from the right side. So you see there's no any boundary. Okay, that's our region. That were actually what we have right now. Okay, so yeah, that's perfect. So that's our region. So we can set up R. So now we are going to minimize the value z, which is y minus x. So y minus x is going to be z value. So what vertices we have right now? I'm going to use red color to indicate vertices that we have up to now. That's actually all the vertices. There are how many? 4 of them. So, and I want to put the coordinates for each one. Okay. So that's 0, 6. This is 0 and 4. That one is actually 4 over 3. Yeah. Yeah, this is 4 over 3 for x. And 0. And the last one is 6 and 0. What I'm going to do right now, I'm going to use z value as the target function and just simply put all the coordinates instead of y and x that stays here and calculate z value. So if I plug the coordinates, z value here, 0 and 6, I just simply will have 6 here. Okay, so if I plug 0 and 4, I'll get z value to be 4, right? If I plug that, I'll get 4 z value 4 over 3. So z value will be equal to 4 over 3. And if I plug that, I'm going to have z value to be just simply negative 6. I'm going to minimize, right? So the lowest value right now, as you can see, it's here. So I just highlight. This is the lowest value right now. Lowest possible value on the vertices that we tested. Actually, if you have a look here, we need to find max and mean value. In our case, because we need to minimize, we need to find only minimum value of those for z, for our objective function, for those vertices. So we found and we figure out that z lowest is negative 6 right now. But the problem is that the region is not bounded. So in this case, because we're looking for a minimum, so similar, we go to step 4. In case of feasible region is unbounded, we need to find if the open half plane determined by that inequality. So ax plus by, so that's our function. In our case, z is going to be y minus x, and z value that we calculate as negative 6 is going to be less than negative 6. That's what we have right now. And what I'm going to test, I'm going to test that this region, the half of the plane, does it have any common point with the feasible region? If it doesn't have any common point, so in this case, we got the minimum value to be negative 6. So let's move there and say, okay, we've got y minus x less than -6. That how we are going to test. So where is that? So first of all, we need to build the line as the boundary. So y minus x to be equal strictly to -6. So that's the line. If y equals 0, x is going to be 6, so it starts from there. And then let's set up a table. When y is 0, you've got 6 for x, and let's say any other point. So let's take y equals 4. If we take y equals 4, we'll get x equals 10, right? So x equals 10 when y is 4. Okay, so we've got 2 points, and I'm going to use, that's the first point, 0, 6 and 0. And when I've got y equals 4, x becomes 10. So where is 10? So 10 is here, and 4. So we've got another point, which is 10 and 4. Okay, so we've got 2 points, and now we're going to connect. So I'm going to use that. I'm going to use just straight line. So, and what I'm going to do, I'm going to connect those 2 points. So that and that point. Okay, this is the line that we have right now. So how we're going to test? We're going to say that if y is basically, so if you rearrange that inequality, you'll get y is less than x minus 6. So basically the region that is common here is that region, right? So I'm going to shade the region that satisfied to that inequality. So basically, if you rearrange, you've got y is lower than the boundary x minus 6. So that's the region, actually. And you can see that this region with our region R have lots of common points, because that is unbounded. It will have infinitely many common points. So what the theorem tells us and what the rule tells us. So if we don't have any common point with the feasible region, minimum value becomes the actual minimum value for z. So if the open half plane determined by that inequality that we have, this one, so it has no points in common. But in our case, we have otherwise case. So z has no minimum value in our case, because we've got common points with our region. So that's an idea, okay? So I hope you understand that. I hope it's clear presentation of how you need to explore your region, your z objective function, and finally your region in case of unbounded region that you have here. Okay, so I hope you like that. That was another example for unbounded region, and next time we just go to problems, real life problems, and try to solve them using that technique. Don't forget to subscribe. That was Daniel Dallas. See you later.